So hi, I'm Josselin Poiret. I'm a PhD student in the GetInEd team in Nantes, and today I'll be talking about mechanization projects for logical relations. Uh, so I'm going to be talking specifically about log-rel-coq, which is a coq formalization, but it's inspired by an earlier project, log-rel-MLTT by Andreas Abel and others. And there's another more recent project that we might also take some inspiration from, but it's slightly different from ours, which is MCTT. And it's more of an NB style formalization. But first, I want to give you maybe a quick refresher on what logical relations are and why we need them. So suppose you want to prove your favorite property for your type theory, which is canonicity, for example. You want to do it by induction, of course, because, I mean, you have judgments defined inductively. So you've got an easy case, for example. If you do some simple computation on positive first-order types, what happens is that you can basically look at the recursive call of the canonicity theorem on the scrutiny, for example, and then decide on which recursive call you want to propagate. So this is a pretty easy case in proof. But if you end up on a higher order type, what happens is that basically here it's the code of the function f that decides how the property on n is transformed into a property on the application. So the recursive call on the function itself, it should return that meta-theoretical function that transforms the canonicity property on n into a canonicity property on the application. So that's basically why logical relations end up looking the way they do. And of course, because we're in dependent type theory, the canonicity on terms, it depends on the canonicity on types. We have to know what the type looks like to know what the property we want on the term to be. So that means that if I have a type in the empty context and a term of that type, I first need to get a witness of what we call realizability of big A. And then using that witness, we get a new relation of realizability of terms at that type. And then we also get a realizer of that term. And more generally, and that's basically the fundamental, what's called the fundamental lemma, for an open term, we basically want to map realizers of the context to realizers of types and terms. So here I wrote it more abstractly, but you should just think of it as mapping realizers of context to realizers of types and terms. And of course, because we have conversion in dependent type theory, and it's important in the typing system, it's used to type stuff in most presentations. We also need to have realizers for conversions, so conversions of types and conversions of terms. But thankfully, we can actually save some work and use only realizers for conversions, because then you get the usual realizers that just looking at reflexive realizers. So that's actually been implemented pretty recently in log-rel-coq by Kenji, who's in the room. And it actually looks a bit nicer. We have less duplication because basically all the congruence rules for conversion are the typing rules that you usually get. But there's a kind of an open thing that you have to decide on when you give a meaning to realizers of types. Because in bare MLTT, the universe is actually very underspecified. You don't have type case, for example. So that means that the universe is not constrained to be positive. So you have actually two choices. You can represent in the semantic model the universe as a positive inductive of, a positive type that's basically an inductive of code. You're just saying, all my types, I know them, they're products, I don't know, sigmas, nats, whatever. Whereas in the negative version, you could say, oh yeah, my types are just things that look like realizer relations on terms. And you have to axiomatize what that means, but you could do that. And it's actually what's done in the literature on paper often. So what the difference is practically is that in the positive case, you can only talk about things that you can encode in the theory. So that's that's less general than in the negative case, where, for example, you can talk about things that do not appear in your system, but that you can talk metatheoretically about. So, for example, you can feed a realizer of a universal quantification on types, a realizer that does not exist in your theory, to get a parametricity result, for example. So that's the main idea behind like all old external versions of parametricity, is that you can bring the meta theory into the study of the system. So the negative version looks nicer, let's say. We would want to implement it, but the problem is we know how to do the positive version. It's actually quite easy. Well, easy. In the logical relations world, it's easy-ish. And in the negative version, we just don't know how to do it. We've thought about it for a while, but basically what you would get is dependent partial equivalence relation hell. So you have transports over realizability relations of types, of realizers of terms, and all that stuff, and a lot of equations around them. We just don't know how to do it. And the problem is, in the literature, they mostly take the negative approach. And they kind of cheat by using quotients, basically. And we don't have quotients. We try to be axiom-free in our formalization, so we can't really do that. So now that we've done all this, we basically just did an evaluator that's terminating in the meta theory. So the main idea behind all of this is we just bring back everything up to the meta theory, and the meta theory is very powerful. So as long as you have enough universes and everything, it just works. But we have no guarantee about correctness of what we've done. So we basically need to add some information to our realizers to be able to trace back the relationship between the realizer and the initial term we started with. So usually you could prove it after the fact, like separately, but what we do in log_alcoc is just construct the evaluator to be correct by construction, basically. So for example, suppose I have some realizer for a Boolean that just says, it's true, but for now I have no information. It's true, but I don't know why. I could add that B just reduces to true under some specific reduction strategy. It's nice because it does give us a relationship between those, but it does not give us a derivation. So there's no proof in the original system that they're equal. So instead I could take that, but reciprocally, it doesn't prove that the reduction strategy works. So we'd have to have a mix of both. So it's kind of interesting to see that we might want to add a lot of different information inside of our logical relation to prove properties we might care about. And basically what log_alcoc does is, I don't want to commit. I'm just going to axiomatize an interface for what information I want to put in my logical relation and do it completely abstractly. I'm going to add some stuff and use the axioms to build a logical relation. Problem is, it's actually pretty hard to axiomatize what we need. We have a lot of axioms, and some of them have changed a lot. Some preconditions have changed, basically because some projects depend on log_alcoc to do their formalization. For example, Martin's talk, he uses log_alcoc. And so it's in flux, basically. It changes every couple of months or so. There's a slight difference that appears. But once we have this interface, a good candidate for our extra information that we might want to put into the logical relation is derivations for an algorithmic typing system, because basically those derivations look like normalized version of derivations in the usual presentation. Because, for example, in the usual system, you can have crazy rules like transitivity, which can make some random type appear inside of your derivation, and you have no information. You just lose everything. The same goes for applications, for example, because it does not let you see into the normal form of your application. It just types the application and stops there. So basically using log_alcoc, what would happen is if you instantiate it with the algorithmic typing system, you take such a derivation and you normalize it into something that, for example, here tells you that a conversion of different function types give you conversion of domains and codomains. That's basically an important property that we might want. But it's actually not so simple, at least in log_alcoc. We can't just instantiate instantly with the algorithmic system, because our version in log_alcoc is pretty weird. It contains also some parts of the original system, which is not nice, as I mentioned. And so if we want to prove that it's actually an instance of our general interface. What's being done in logalcock is first, we have another dumbed down algorithmic system. We do the logical relation fully once. And with that, you deduce what's needed to instantiate with the full algorithmic system. I don't know about you, but I think it looks messy and very unprincipled. We would like to just have one pass through the thing and then be done with it. So that's basically what my opinion on it was, and I wanted to find some alternative to the algorithmic system in logalcock. And of course, the abstract, if you read it, mentions some alternative freestanding systems. So I say freestanding because it should not include anything about the original specification. It should be completely separate. That types things by first normalizing them. So of course, as you might know, you can't just willy-nilly normalize something and then type it, because you're going to erase some information that might have made the term not type checked. For example, here, if I normalize away this beta redex, then I'm going to lose the fact that these two do not match up, the argument and the signature. So what I settled on doing at first was having some kind of well-typed reduction that would check things as it reduced terms. But basically, that incurs a lot of additional work. And I realized that instead, you could just have a very narrowed version of algorithmic typing followed by reflexivity for the algorithmic conversion, because the algorithmic conversion gives you the deep normal form information about your term. So I kind of dropped my weird system and instead tried to focus on the algorithmic versions. And you would need to disentangle it with the declarative system that's more nasty. So maybe if we want to take some questions, I'm gonna stop with a conclusion. So basically, we are still far from, even though it's a good effort, we are still far from having all the results that appear in the literature. And it's, for now, we can't really expect to tackle more complex systems. So I'm thinking of course, cubical type theory, for example, but even simpler systems, they would be pretty hard to implement in logalcock. And we'd need to really think hard about what frameworks we want to have, and also clean up the main techniques and have them more principled to be able to tackle those more complex systems.